This is section 5.6. We're looking at triangles. Triangles can be classified or sorted in a couple different ways. For the first example, we're going to classify them according to the sides that they have. First way, or the first type of triangle, I guess I should say, is a scalene triangle. And scalene triangles have no equal sides to them. And so I always think of like drawing a carrot nose like Olaf on the snowman. Just looks kind of out of sorts a little bit because there's no equality to it. Our second type of triangle is our isosceles triangle. The isosceles triangle has two equal sides. And so let's draw one that has the left and the right hand side equal to each other. And I'm sure you're guessing where the last one is heading, equilateral, and you can even hear the word equal in it. We have all sides equal for our equilateral triangle. And since all sides are equal in an equilateral triangle, actually all angles are equal as well. We can also look at our triangles by looking at the angles. We know that an acute angle is less than 90 degrees, so an acute triangle has all angles in the triangle less than 90 degrees. So that triangle that we just drew, that equilateral triangle, fits the description. Next, we have our right button. We have our right triangle. And just like our right angle is 90 degrees, we have one angle in a right triangle equaling 90 degrees. And so, again, I drew that symbol to show you that my bottom left-hand corner is my right angle. We know obtuse angles measure greater than 90 degrees, so an obtuse triangle obviously has one angle that's greater than 90 degrees as well. So here's an example of that. The mathematical notation for angles was introduced in section 5.1. Geometry also has specific notation for triangles. And it's going to walk us through the same thing as it did for angles. The symbol for a triangle is a small little triangle, go figure. And so when we see this symbol with ABC next to it, we would call that triangle ABC. And it says a triangle is named by listing the angles in order as you move either clockwise or counterclockwise around the figure. So let's name the different ways. Well, we already know that it can be called triangle ABC. So that's starting with A and going counterclockwise. But if we went clockwise instead, we would call it ACB. We could also start with point B, and if we went counterclockwise, that would be triangle BCA. Or if we started with B and went clockwise, it would be BAC. Or we can start with corner C, vertex C. And if we went counterclockwise, it would be CB. Well, I guess that is clockwise. If we went clockwise, we would go CBA. Or we could go and do CAB. So there's actually 6 ways that we could name this one triangle. Now we're going to look at a couple things that are true of all triangles. The measure of all the angles added together, or the sum, is 180 degrees. We'll prove that in a minute. Another property is the sum of the lengths of any two sides must be greater than the length of the third side. And then the third is the longer sides are opposite angles with larger measures. Let's prove that a triangle angles all add up to 180 degrees. So what is the angle measure of a straight line? We know a straight line is 180 degrees. Here they give us two parallel lines that make up, oh, that's really not very pretty, is it? That's better. The space that the triangle is in between is through those parallel lines. And then it asks us, what do we know about the sum of measure of angle 1, the measure of angle 2, and the measure of angle B? So here's 1, here's 2, and here's B. So those three make up that straight line, or that straight angle at the top. So the sum is equal to 180 degrees. And then it asks us about alternate interior angles. Remember, alternate interior angles are across each other from a transversal. So if we look at the left side of our triangle as a transversal, alternate interior angles would be angles 1 and A together. And then if we look at the opposite side, our right side of our triangle, as our transversal, we can see that angle 2 and angle C are alternate interior angles as well. So what do we know about alternate interior angles? They are equal. So if we know that angle 1 plus angle 2 plus angle B equals 180, and we substitute, since 1 is the same measure as A and 2 is the measure same as measures of angle C, then we can say that A plus B plus C equals 180 degrees as well. So the sum equals 180. And we prove that with our parallel lines and the definition of alternate interior angles. Similar triangles have two properties. First, corresponding angles have the same measure, and second, the lengths of the corresponding sides are proportional. And notice they show in the diagram which angles are corresponding. Here, they use 1 mark to show that angle B and angle Y are corresponding angles. And then they use 2 marks for angle A and angle X. And they used 3 marks to show that angle C and angle Z are corresponding angles. And so they're telling us that angle triangle ABC is similar to XYZ. Notice there's a little squiggly mark in here. That symbol says that they are similar triangles. And we can set up proportions in that relationship. Usually when we look at proportions and think about them, we do 2 at a time, but this shows that we can take any of the sides and show that they're proportional. AB compared to XY, so they're showing the left side over the left side, is the same as BC over YZ, so right side over right side, is the same as AC over XZ, the bottoms. Now, as you know, I like to compare triangle proportions to other triangle proportions, or one idea to another. So what I would do, for example, is I would say for my proportion, first triangle, let's say we're comparing left side to right side. So AB compared to BC is the same proportion as left side of the smaller triangle XY is to the right side YZ. Same results, same answer. I just like to go one triangle at a time. And if you notice here, we would still have the same multiplication problem, that we have AB and YZ being multiplied because they're across from each other, and BC and XY being across from each other. So we still get the same answer, but again, it's just a matter of preference and how you like to set up your proportions. When writing the names of two similar triangles or two congruent triangles, it is important to write the corresponding vertices, remember that's just the corners, in the same order for both triangles. That means that for triangle ABC is similar to triangle XYZ, A corresponds with X, B corresponds with Y, and C corresponds with Z. So they're in the same spot in the triangles. A common mistake when writing the notation for similar triangles is to incorrectly match up the corresponding angles. Determine if any mistakes were made in the notation for each pair of similar triangles. And if there was a mistake, it says describe it and then write the notation correctly. So if we look at our first triangle in its notation, it's calling this triangle ABC. So we started naming here, and we went counterclockwise to B, and then stopped at C. So that means we should be doing the same thing. And so X, Y, Z here, they started naming it at X, then they went to Y, and then they went to C. So going counterclockwise, put the alphabet in order as far as A, B, C, but when we look at our second triangle, the letters went clockwise. So it's X, Y, Z going the top vertex, the lower right, and then the lower left. So that is not correct. In order to make it similar, because again, the notation is showing it differently, is that the location is right, and we need to go around this way as well. And so this would be named as triangle X, Z, Y, because B corresponds with Z, not with Y, according to the picture. So for our second one, we have D, E, F. So this time we're going this way. L, N, M, L, N, M. We do the same pattern. So that one's good. There's no mistakes made for the second one. Congruent triangles. Congruent triangles have two properties. Corresponding angles have the same measure, and the lengths of corresponding sides are equal. Notice the symbol now is that similar triangle squiggle, but an equal sign underneath it. And so when I think of congruent triangles, I think of it being a carbon copy. It's like if you're in Microsoft Word or in PowerPoint or something and you want two of something picture, and you right click on it and hit copy, then move over, right click and hit paste. So you'll have two identical things. Where similar triangles is like taking a picture or a photo and blowing it up. So maybe, on a copy machine, you have it set to copy it at 150%. So the proportions don't change, just the size of the side. The sizes of the sides change. Now, when you have two different triangles, you need to be able to prove whether they are congruent or not. And there's three different ways of doing this. We have side angle side, which means that all sides are the same length. And if all sides are the same length, then we have congruent triangles. Then next we have side angle side. That order is important. Two sides of one triangle and the corresponding side of the other triangle and the angle in between them. So side angle side, if we draw a triangle, would be saying that we have this side maybe and this side, but we have to include the angle in between. Because if we chose a different angle, we couldn't read it around the shape as side angle side. We can go clockwise and still say side angle side. But for example, if we were taking this angle instead of this green one here, we would name that as maybe angle side side or side side angle. And that's not the same. That cannot prove that two triangles are congruent. We have to have that angle that's in between them. The sides make up that angle. But then we can also use two angles and one side, but again, the side has to be between it. It has to be the common side of those two angles for it to prove congruency. So for this one, we would have a triangle, and let's say we have this angle here and this angle here, so that common side would be this side over here. So we would have angle and the side and then the angle. So those are the only three ways that you can prove a triangle congruent. So let's take a look at some skills checks problems, these practice. Since we haven't done any of these practice problems together, any similar exercises, we're going to do them together now. Our first direction says to determine whether or not a triangle with the given dimensions exists, if it is possible, using the second property of triangles. Remember, the second property of triangles says the sum of two lengths of a triangle has to be larger than the third length. And so we have sides 4, 5, and 7 inches long. So what we're checking is that 4 plus 5 has to be bigger than 7 in order for these three side lengths to be able to create a triangle. And when we add 4 plus 5, we get 9. 9 is bigger than 7, so that's true. It will work. For our second one, we have a side length of 9, a side length of 32, and that has to be greater than the longest side that they give us of 41. 9 plus 32 is 41. So this is saying that 41 is bigger than 41. That is not true. And so this is no. This cannot create a triangle. What would happen is if you had that length of 41 down here and you hold up the side of 9 here and try and put that side of 32 over here, they're just going to fall down. They're going to end up touching and then just create the same length that you had on the bottom. They won't be able to touch each other to support each other to actually create a triangle. And then for 7 and 8, we need to say whether they are similar or not. Similar doesn't mean identical. It means that they have a relationship with the angles being the same but not necessarily the sides, but they has to be in proportion to each other. And so if we look at question 7, let's start comparing the sides. We have our left side equaling 4 and the right side equaling 4. So the relationship there is that they stayed the same. If we continue counterclockwise, we see that the base is 2 and then the base is 2 as well. So far, so good. I mean, they would be congruent right now as far as our book, which we are okay with. But then when we get to this third side, we get a side length of 3 and a side length of 4. So they changed only one side, so that kind of skews it. So the answer is no, because of those two lengths, there's no way that they could be similar triangles. Number 8 doesn't look like they're similar when I first look at it, but let's go through what we know and what we have and see what we get. When I look at these two triangles, I see that they're created by somebody drawing an X to start off with. And so when I think of it that way, I see vertical angles here. You might not remember that name, vertical angles. Remember I mentioned them maybe as kissing angles. So it reminds me of, and they are congruent. So we have 110 degrees being identical. These two angles in here with vertical angles being identical, and we know the sum has to be 180. So by that property, angle B and angle D have to be the same size. We don't care about the length as long as all three angles are the same size. Yes, they are similar triangles. So it's just turned where A would be similar to E. So let's even write that. So triangle A, and then congruent. And we'll start over here with E, because we have to order them to show which angles are similar to which angles. So if A, let's go to B next, which we labeled with an X. So in our other triangle, it would be D. And then our two kissing angles are just both at the C point. So let's have triangle ABC is similar to triangle EDC. Now we have to determine whether we have congruent triangles and state the property. And they give us those properties here for us to look at to remind us. All sides have to be the same, two sides with the angle in the middle, or two angles with the side in between. And so if we look at our first set of shapes, we can see that everything matches up, but we have to go around and make sure they're all in the same spot, and it follows one of these rules. So here we have 10, and if we keep going counterclockwise, we have an angle of 110, and then we have a side length of 7. So we have a side, an angle, and a side. So SAS, side angle side, is one of those. So that's what we're checking for. And we can see that, yes, this one follows that exact same pattern. Side, angle, side. So that's our side angle side property. For our second one, we see all lengths around the outside, and they're all in this exact same spot. So that is going to be our side, side, side. And the same thing as with 11. The 6s pair up, the 10s pair up, the 9s pair up, and they're all side lengths. So side, side, side is the easy property to be able to use. But let's look at number 12. Let's start with the 55. That's an angle. And we'll continue to go counterclockwise. And so we have now a side length. And then the next thing that's given to us is another angle. And so when we read that, we get angle, side, angle, which is one of our possibilities for proving congruency. So let's make sure that we can get that angle, side, angle from the second one as well before we call it a good answer. So angle from the first one was the 55 degrees. So here's our angle. Then we moved on to the side of 15 feet. So far, so good. Here's our side. And then it went to the angle that's 65 degrees. And so that works. So all they did is just kind of flip the triangle over, push that top over to the left-hand side and down. And it's still a congruent triangle because of the angle, side, angle properties. Now let's use our information that we've learned about triangles to answer some story problems. A building has two ramps going up to the entrances located on opposite sides of the building. Both ramps have an incline of 4.5 degrees and form a right angle with the building. The first ramp has a base length of 8 and the second ramp has a base length of 15.25 feet and a height of 1.2 feet. So they drew a nice illustration for us. Do these ramps form similar, congruent, or neither? Okay. Well, we know they're not congruent because congruent, we have to have all side lengths the same. And for the base of one, it's 8, and the base of the other, it's 15.25. So we know that's not true. Neither or similar are our next two choices. Well, let's look at the other information that we're given. We have a right angle measuring the same as a right angle, 90 degrees. Then they told us that both ramps were at 4.5 degrees. So if two sets of angles measure the same, then the third, because we know the sum has to equal to 180 degrees, are the same as well. So they are similar because they have the same size angles. And then it asks, what is the height of the 8-foot ramp? So we can use our idea of proportions to do that, to make sure that we're lining things up. So if we look at our 8-foot ramp, we need to know the height compared to the bottom of 8. And so that has to be the same as our height of our second ramp, which is 1.2, compared to its bottom of 15.25. And that gives us a proportion that we know how to solve. So the 15.25 gets multiplied to our unknown height, and the 8 gets multiplied by the 1.2. So then that gives us that 15.25H is equal to 9.6, and we'll divide both sides by 15.25 to get H by itself. And so that gives us the height of the ramp is 0.63 feet. The pieces to assemble a spice rack include two congruent triangles. The triangles need to have corresponding angles lined up. Match the corresponding angles on the triangles. Write that the two triangles are congruent using proper mathematic notation. So let's start with our first triangle. We have, let's call it ABCs to keep it in order alphabetically. Our congruent is the equal with a little squiggle on top. But now we need to make sure that we mention the angles in the same order that we did ABC. Angle A was a 60 degree. So our 60-degree angle in our second triangle is angle E. For our second angle, angle B, we have 50, and so we need to go to our 50-degree angle in our second triangle, which is angle F. And then lastly, we have C, which was our 70, and so our 70 angle for our second triangle is G. So angle G and C are congruent. So triangle ABC is congruent to triangle EFG. Would it be enough for the manufacturer to label just one corresponding angle on each triangle? That is, can you determine how the other angles correspond just by knowing one angle corresponding? And the answer is no, because what if you accidentally flipped one triangle over? Then it would switch which angles get paired up. Just like in this picture, it looks like A should be paired to C, or I'm sorry, A should be paired to G, just if we look at locations, but it's not. So I'll just call it being flipped. So again, it's just like taking a piece of paper and turning it over. So even if the top stays in the same spot, the left-hand side and the right-hand side is going to switch sides. A billboard advertisement has a right triangle as part of its design. In the scaled version that the graphic designers made, the base of the triangle is 8 inches and the height is 5 inches. And so for our scaled version, we have a base of 8 inches and a height of 5. And I'll even put B for base over H of height. Make sure I get the second measurements in the same spot. On the full-size billboard, the base of the triangle is 96, so that goes in the numerator. What is the height of the triangle? We don't know this height, so that's going to be our unknown H. So we'll do our cross multiplying to get 8 times H is the same amount as 5 times 96, and then solve it. So 8 times H will equal 480. And then if we divide both sides by by 8, we will get H by itself. And that leaves us with a size of 60. And if we look back at our problem, we can see that 60 is in inches. So the billboard is 60 inches tall, or 5 feet tall. We have 2 more questions to go. A handicap ramp must be at an angle no greater than 4.76 degrees from horizontal. And so what is the measure of angle X? And what is the relationship between the 4.76 degrees and the angle X? Well, we're going to use the answer to B to help us with A. We know that the total degrees add up to 180. Well, we know that this right angle here is 90 degrees. And we are given the 4.76. So we could take the 180 minus 90 minus 4.76. But if you start subtracting, you 180 minus 90, you'll see that there's 90 left. And we know that 90 degrees are complementary angles. And so instead of having to do 180 minus 90 minus 4.76, we can just do 90 minus the 4.76 to say that the measure of angle X equals, and when we subtract, we get 85.24 degrees. Because again, in a right triangle, the two angles that aren't the right angle are complementary to each other. And for our last problem, we have a historian needing to determine the height of an abandoned lighthouse. Since he isn't able to directly measure the height, he determines it indirectly. Using a 2-foot-long stick in the ground, he measures the length of the shadow it casts, and then he measures the length of the shadow that's created by the lighthouse, and that will help him determine the approximate height of the lighthouse. And it says, note that the stick and the lighthouse are both at right angles. And so we are able to set up a proportion with the height compared to the shadow length. So for our stick, we have a height of 2 and a shadow length of 0.75. And that needs to be in the same proportion of the height of the lighthouse compared to a shadow of 55.5. And we'll cross multiply to get that answer. So our 0.75 is with our h. And that should be the same as 2 times our 55.5. And so 0.75h is the same as 111. And so when we divide both sides by the 0.75, we see that the height of the lighthouse is approximately 148 feet tall. So there are a few examples of story problems using triangles. As always, if you have any questions and problems with your homework, let me know. Do a screenshot and send it to me via email, and I'll be happy to help. Otherwise, we'll see you next time.